This video is going to be on one a day 6 for differential equations, Math 365. So basically, I'm going to kind of go over the whole lesson or the whole notes. I feel like maybe that can help explore and explain some of the challenges that we may have encountered during our time at this week. All right, so first of all, under the acceleration models, we're going to get our first start on an idea around this is our globe, and this is the radius of Earth. Imagining a mass somewhere up here, it's a mass of little m, and it's some distance from the center of the Earth of radius r. And I'm going to use capital R instead of Z and Z naught to recognize the height here, just to kind of keep it in a different notation that may be more helpful than the Z notation I typically use in this regard. Okay. All right. From Newton's second law, we have the force of gravity. For Newton's gravitational law, we have F of mg. F of g is equal to negative mg m over r squared. This is the magnitude, but it is directionally pointed towards the center, so the force is technically pointing down into the center of the Earth there. All right, and we have the mass here is the mass of, in our case, the mass of Earth. Capital is the mass of Earth, and the big G here is the gravitational constant, and the little n is the mass of our particle here, and the radius is as indicated. All right, this is going to be equal to the masses from Newton's second law of dv dt, where we normally would consider this a product of m and v, or the momentum, but assuming mass is constant, then the dv dt is simply the rate of change of the velocity, which is better known as acceleration. Okay. Note here that dr dt, the rate of change of our radius, is the velocity. And so that can really nicely allow us to find a first integral of this particular problem almost immediately by doing a quick realization that we have dv dt using the chain rule is dv dr dt, which is then v dv dr. Oh, that looks like another dr. There we go. Okay, so now we have dv dr and the velocity. And the reason why that's nice is because on the other side we have a different an equation with r, and so this becomes a separable differential equation. That's going to give us our first integral, since the independent variable is missing in our second order differential equation. We've reduced it to a first order differential. And so plugging everything back in, realizing that the mass here and the mass here are in common on both sides, so we can reduce that even further. And so we get negative mg. Let me see if I can move it over here. Negative mg over r squared is equal to, looks like v, with the m canceling, dv, and we have a dr on this side. Okay, integrating both sides and realizing that our radius here has to stop when it meets the lower radius has to stop when it meets the big R here. So then we have the integral of negative mg over 1, the integral from capital R to lowercase r, where this r is some arbitrary point. I'll call it d script r over r squared. That's the case for here. And then the integral of dt. All right, simplifying this, power rule and power rule, this is easy to see that this becomes mg over 1 for now, 1 over r minus 1 over capital R, where capital R is the radius of the Earth. Okay, getting a common denominator and simplifying this a little bit, I'm going to write the right-hand side over here on the left-hand side, since this integral is just simply t plus c. that is the result of the integration from there. Getting a common denominator, we get mg. This is going to have capital R minus lowercase r over r times big R. And then this r here is what I'm going to move outside in this placeholder position there. And so if I do that, then this simply becomes big R. And so notice that these are all constants with respect to the Earth, basically. Mass and radius, and then g is the universal gravitational constant. In case you're wondering where the negative went from here, when I integrated this, the power rule, bring one up, you get a negative one, and bring it down, you get a negative one, so the negative cancel, which is why this is positive. Okay? All right. Oh, I have it as t. That should be v. And that should be v. There should be a v there as well. Oh, I am making all kinds of mistakes there. There we go. There it is, v dv. All right, and then integrating that, you're going to get v squared over 2 plus c. There we go. That looks better. Okay, which means I can then move the 2 over to the side as well. So let me do that first. I'm going to have v squared is equal to 2mg over r times capital R minus lowercase r. Okay. Now, the nice thing is here is that, remember, v was dr dt, and so this has still a function of r, and I can make this as a function of t, so it's still separable. I'm going to take the square root of both sides, and then flip that over, flip it over, take the reciprocal, and that will get me dt. If I do that, dt is going to be the square root of flipping that over, r over 2mg. And then what do I have here? I have move this up. I have the square root of r over r minus lowercase r d r. All right, it's at this point in the notes, like I said, we're going to let r equal capital R cosine square theta. And doing so will help us cancel out quite a few things. So dr, we're going to have a product rule here, product rule, power rule, it's part of the chain rule. So we're going to have a little bit more room. So dr is going to equal 2r cosine theta and the negative sign theta d theta. Okay, so that's the dr that we have. And I'm going to really focus in on this part right here before I plug in the dr, just to simplify this piece. And then we can plug everything back in. So this is going to be r cosine squared theta. That's the lowercase r divided by r minus r cosine squared theta, plugging in for r cosine theta. Now notice that they all have an r in common, so I can reduce that. And then this is going to give me cosine squared theta over 1 minus cosine squared theta. 1 minus cosine squared theta by the Pythagorean theorem for trig says that this is sine squared. And so that's really nice because now I have cosine squared theta over sine squared theta. And remember, this is underneath the square root. So if I take the square root of both of those, that's going to give me cosine and sine. We will assume that our angles are appropriate so that the sines, cosines are not negative, even though they are being squared. So we don't have to worry about the absolute value. And we take the square root, and if we do that, then this whole thing becomes the square root of dt, the square root of r over 2mg. That's going to be cosine theta over sine theta. And then dr is going to be all this, which is negative 2r cosine theta sine theta, theta. Simplifying again, a sine is going to reduce here. You get a cosine squared. The cosine squared is the same thing as the square root of r over 2mg. You have a negative 2. Let me move that negative in front because that will stick around. But the 2 is going to cancel with the 1/2 from the cosine squared, giving us 1 plus cosine of 2 theta d theta. And now that can reduce. So this gives me a cosine squared from these two. And this is the power reduction formula. Sorry, was that a view there? So this cosine and this cosine are cosine squared. And then using the power reduction formula, uh, cosine squared theta is equal to 1/2 1 plus cosine 2 theta. That's what I'm using there. And then the 1/2 and the 2 are going to cancel, which is great. So I have a negative the square root of r over 2 mg. 1 plus integrating this is going to give me theta. So integrating this finally, I'm going to get theta, and then here I'm going to get a half out from the u sub that I would make there, and then the integral of cosine is sine 2 theta, and that would be it. And then I have a d, I have a t plus t on that side. All right. So now our integrals in terms of thetas, I need to get rid of those. Going back to our original result here. We had that right here, that r over r is cosine squared. So the hypotenuse here is square root of r. The adjacent side is the square root of little r, which means this squared minus that squared. And the square root is going to be the opposite side. And then sine of 2 theta is going to be, can be expressed as, this is going to be negative square root of r over 2 mg theta plus 1/2 times 2 sine theta cosine theta, using the double angle formula for sine of 2 theta. So the 2 cancel, and we need to find sine of theta and cosine of theta. So let's see. Well, cosine theta is really easy. That's the square root of r over r. And so cosine squared theta, if I use that. Yeah, I don't know. Maybe I can just do it that way. Then it'll be easier. Okay, the cosine squared theta is 1 minus is equal to sine squared theta. And you know what cosine squared theta is? That is 1 minus the r over r. That seems fair. And maybe we can absorb the negative in there. Yeah, we can do that. So if I distribute that negative through, then I can, yeah, negative. So we have 1 minus r over r. And if I take the square root of that, that implies that sine of theta is equal to the square root of 1 minus r, which is exactly what it says. Yeah, as it should. That's a different way of doing it. I like that. It's kind of fun. Okay. Nice. So we have that's sine of theta and cosine of theta is. So we have that this is negative the square root of r. So I'm not going to distribute this as that I might be able to absorb the negative in there, but it looks like I won't. So I have cosine inverse, or arc cosine of the square root of r over capital R, and then plus sine, which is the square root of 1 minus r over capital R, and then times cosine, which is the square root of r over r. Let's see, looks like I can distribute that through. So there's the r here, I'm not sure what that is. 2. So there's an R, there's an R, there's an R. Oh, it seems like we're missing a term there, so I need an R over here as well. So it goes there, goes there, and then it comes here right there. So it didn't go anywhere. Okay, and that's equal to T plus C. And then we can apply the initial conditions to find out if we plug in R equals R, for example, then R equals R, this is going to give me 0, this will give me 0, so that gives me then that at T equals 0, C is equal to 0. So this implies at T equals 0 with R equal to R, then C is equal to 0. Okay, so that's one conclusion that we can make. Should that be the initial conditions we're looking at? All right, we're going to expand on this derivation. This is exactly how you would go about solving, I think it was like the first problem in the problem set. The next thing we wanted to look at with regard to this problem is with respect to escape velocity. So I'll clear off the board and we'll talk about that in more. All right, we're going to look at escape velocity now. Okay. So we're imagining if this is like the surface of the Earth, that our thing gets fired up. And so we're trying to figure out what's happening. Can't tell if it's a flat. If you see it as a rocket anyway. So we're going to look at dv dt is equal to d squared r dt squared, which is equal to negative g m over r squared. Okay, so that should look familiar. And like before, we can exactly pull that this implies that dv dr times the velocity is equal to negative g m over r squared. So nothing new here. And if we integrate both sides here, just like we did before, we're going to get v squared over 2 is equal to gm over r plus a constant. Okay, so there's not a lot of new here. The only thing that we didn't talk about is that before we had this was a definite integral, and now we have an indefinite integral. Okay, so now suppose that v is equal to v naught, so that's our initial velocity. And for our intents and purposes, I don't have the picture anymore, but our intents and purposes, imagine that r is essentially we're firing from the surface of the Earth. So r and r, the radius, the capital R, is the same. Okay, when t equals 0. Okay, so it's fired with an initial velocity, but its position is at r equals r. Okay, and so if we plug that in, let's see, we would have v naught squared over 2 is equal to g m r plus c, which implies that v naught squared over 2 minus g m over r is equal to our constant. And so if we plug our constant in, we're going to get that v squared is equal to v naught squared plus 2gm over 1 over r minus 1 over r. For any height later, right? So as the time goes on, this thing goes up. Okay, so we want the implicit. Yeah, that was a nerd little hiccup. Sorry, trying to figure out how to word this. So v squared is going to be greater than or equal to v naught squared plus 2gn over r minus that. So now we found c. Let's plug it back into our equation that we found here. We have v squared over 2 is equal to gn over r plus c, which was v naught squared over 2 minus gn over r. All right, so looks like we multiply everything through by 2 would be our first nice simplification. And then we have v squared is equal to, now these are off by a sign, but the both have a gm on top and both have a 2. So it looks like I have a v naught squared. That's the first, the 2's will cancel. And I have plus 2gm. And then I'm going to have 1 over r minus 1 over r. Okay. And now, let's see. Well, we know that v squared will be greater than v naught squared minus 2gm over r. So if r is really, really small, for example, or really, really large, I really want to see it, we know that this is true. Okay. Which means that, well, as long as, so this is going to be true, meaning our velocity will be greater. It'll be enough to escape, since that's what we're trying to do. This will be bigger than 0, provided that really we need v naught squared to be minus 2gm over r. We need this bigger than 0. Yeah, so the term starts to dominate, then this becomes less, which means this will be less, and eventually they'll reverse the velocity and make it come back down. So we definitely want this to be the case. We need this to be at least greater than or equal to 0, not necessarily strictly greater than. Okay, which implies then, it looks like if I move this over, I get v naught where it's greater than or equal to 2gm over r. Taking the square root of that, we're talking about the velocity, speed really. That v naught got to be greater than or equal to the square root of 2gm over r. And that would be then the requirement for the escape velocity. Okay, so let's run that back through just to make sure we're all on the same page. Okay, so if this is true, then that means that this inequality is true, that this will be greater than or equal to 0, which means that this quantity is going to be positive or increasing, certainly bigger than 0, which means that this velocity is going to be great, if it's greater than, means it's larger than this, which means it will be going to be able to go faster and escape the gravitational pull. So that's the thoughts on the chain of reasoning here. Okay, in other words, if this becomes less than 0, that means that while this is still true, the actual velocity is decreasing, and so it may at some point cause it to the inequality to switch directions, and then the velocity would go to well, it'd come back down to Earth. Okay, hope that was helpful. And now we're going to move on to the next example, and so that clear off the board. All right, in our next example, we're going to be talking about air resistance. And so this one is anything that has something that's proportionally to the square of the velocity. So some resistant force that is pushing against the movement of something. Newton's second law would tell us that F equals ma, which is equal to m dv dt, as we've seen before, assuming the mass was constant, which is going to equal, so this part is going to be equal to the force of gravity plus some potential something that's proportional to the velocity squared. So this is a dragging force that is opposing the motion. Okay. So like wind resistance, for example, would fall into this category. Okay. All right. So what do we do with this? Well, we can simplify. We know that we just look at this bit right there. I can divide through by the mass, and I would have dv dt is equal to minus g over m, not dw, v squared. If you're familiar with uh, Hooke's law, this has a very familiar form where the resistance there is the potential caused by the spring constant. This has a very similar feeling to it. The good thing is that this is g is a constant at this elevation, if you will. This is our constants, and so the only thing that's not the v squared. We have a dv over here, so this is separable, and so I can divide everything through this term, and that gives me then that dv is going to be negative g plus k over n v squared is equal to dt. All right, so now we have this separated. This is an integral that should look fairly familiar. This is this is the derivative of a known antiderivative. And this side is just the integral of the power rule. So making the appropriate substitution on this side, the resulting integral gives you the square root of m over gk, and inverse the square root of k over m g v is equal to negative t plus c. Solving for v, we'll take the tangible side, multiply through by this as well. And in doing so, we get v is equal to the square root, the inverse of that. Right. Well, sorry, it's the inverse of this. So you get g n over k. That can be here, so that's the argument of the tanh function. And we have a new constant, let's call it c. Yes, another c minus the square root of g k over n times t. And if we assume that e, okay, so here's a function of, and so to find the constant here of this particular integration, if we assume that at time t equals 0, at time t equals 0, we have v naught as our speed. That will allow us to solve for this constant. So plugging that in, that's 0. This is v naught, these are our constants. We get that this c is equal to tanh inverse of v naught times v square root of k over mg. Okay. And finally, putting everything together then with this, assuming this initial conditions are true, then v of t is finally going to be written as the square root of gm over k times tanh of tanh inverse of all that loveliness, v naught square roots of k over mg, and then minus the square root of g k over n times t. And so that then is how the velocity will be affected by a resistant force, like a something proportional to You can also find the terminal velocity here. Just one last little note to maybe highlight. Since tanh is the sum of exponential functions, namely tanh of x is equal to e to the x minus e to the negative x. Just like it's trig, it's non-hyperbolic or it's sine over cosine. It's a sinh over cosh. So e to the x. They're both divided by 2, which is why the 2's cancel out, and you're just left with the sum and difference of the exponentials. But notice that these are real values instead of the imaginary that you would get with sine and cosine. So with this representation in mind, and if you wanted to consider the terminal velocity, so this would be what the velocity of this function would be at a much later date. Take the limit as this t goes to infinity. Computing that, you'll get that the limit of v of t as t goes to infinity actually approaches negative the square root of g n over k, which is the terminal velocity, which is kind of cool. So this is the terminal velocity in its expressed form. All right, I hope that was helpful, and we will see you in a second for an actual example and compute that, and then we'll wrap up this video. All right, in this example, we have that a 200 kilogram mass, that we'll call M, is dropped in a media with a drag coefficient. So we have a drag coefficient, K, equal to 0.0, oops, sorry, no, not 0.0, but 0.15. Assuming the object falls under the influence of gravity, we want to find the terminal velocity. Okay, so we're after terminal velocity. Okay. So we saw from what we just finished that the terminal velocity is going to be equal to the square root of m k g over k. Oh, I guess I should explain. When I see the m and the k together, I think of if you've ever seen, oh my gosh, South Park. Okay, so that gets stuck in my head and I can't stop saying it. So the velocity is going to be the terminal velocity will be the square root of mg over k. So if we plug in the amount values that we know, that should be g 9.8 over 0.15. Plugging this in, computing it in the calculator, you get about negative 114.3 meters per second is the terminal velocity that we're expecting for this function. Okay. And let's plug this in. So we call from the earlier problem that v of t, I'll look like a u. V of t is equal to the square root of mg over k tanh inverse v naught square roots of k and g minus the square root of gk over n times t. Okay, so that's what we're using. Note that we're assuming, since it's not explicitly stated, that v0 is equal to 0, which means that this term actually is equal to 0. So we won't need to input that into the function, which greatly simplifies v of t. That's going to be mg over k. tanh negative square roots of gk over m t. Okay. All right, let's go ahead and jump over to GeoGebra and we will take a look at what this function looks like.
All right. So
let's actually it's probably just to define the quantity. So m is equal to 200, g is equal to 9.8, k is equal to 0.15, and then we can just plug it in. So we have the square root of mg over k times tanh of negative square root of vk times k over m. Oops. T. Okay. And then we do zoom to it. And kind of zoom it out. Oh, let's do in a domain. Let's restrict our domain to just t greater than 0. Okay. So then if we do zoom to fit, that would give us a better little bit. Zoom out a little bit. Okay, so you can see that there's the limiting factor, and if we did the terminal velocity negative square root of m times g over k, you can see there that that is the limiting value. So if I plot that y equals a, you can see that those are the terminal velocity and how it approaches that value. All right. I hope that was helpful. And we're going to jump on to the next example. We're going to look at variable mass. This is one that may cause some of the most challenge, but I think it's also one of the coolest. So this is a case where mass is no longer constant. And so Newton's second law, F is equal to dp dt. And previously, we would say that the mass is constant. This would just be the change in velocity. But when mass is variable, then it's also changing with respect to time. And so this is mv. And so then this providing or following the product rule is going to be the sum of, or the product of two things. So we get a sum with the changing. So we have dm dt times the velocity plus m times dv dt. And so that's the new bit here, is the change in mass with respect to time. So that's really cool. So let's do an example with this one instead of just explaining or deriving some sort of solution to something. So in the example we have in the notes, we're looking at a chain. So this example, you can imagine it's a windowsill, but imagine it's just like a table. So here's the window. There's this pile of chain, and then that part of the chain falls off. So it's falling off to the ground like so. And so if you can imagine that we measure this imaginary height here, this is x. We're going to take that to be the length of the chain as it's moving down. So let x equal the length of the chain that has left. It's left the windowsill, or the, yeah, windowsill. Okay. It's the length of that chain. I guess I should also say that it's n in motion. Okay, so it's the bit that's moving. So it's this bit right here. It's this bit that's moving. Okay. So you can imagine a chain like in a thing that's being pulled over and it's falling down and falling down, falling down. Okay. So that's the length there. As the chain falls, okay, we're gonna assume that the weight is per pound of or per foot. We're gonna call that a density, and that's gonna equal the weight in pounds per foot. So in other words, the more the chain falls, the heavier it is, right? So so that's kind of the idea that this is a changing mass, that as more and more of the chain falls off, there's gonna be more and more weight accumulating, which should make sense. Okay. All right. So we have this row of x. So this is going to depend on our variable that we've defined here as x. So rho is a function of x. Okay. All right. So back to the problem then. Let's assume that our windowsill is pretty high up. We're going to say it's 100 feet up from the top to the bottom. So there is our height, and we want to know. Okay, so it begins at rest. Actually, right? At rest, meaning v naught is equal to 0, which is great. And there's 10 feet. It's in the problem that says already played out, which means it's already 10 feet in motion. In, let's say, motion. That means that it kind of like maybe it got entangled a little bit somehow, and then when it got to 10 feet, that's when it was enough of a weight on the thing to start really pulling it down. Okay. All right. So what do we have going on initially? So we have mg is equal to rho x. Those are the forces initially acting on it, or um, that's true. It's rho x. I forgot to. It's a multiplication of x, so it's rho per feet times how many feet gives you that. So that tells me then that m is equal to rho x over g. Remember, rho is a function of x as well. Okay, so that's really helpful because now that we have m as an expression of mass, we can figure out how mass is changing with respect to time. Going back up to this value here. So dm dt is equal to dm dx dx dt. dx dt is the change in length, and dm dx, if you look up here, it's going to be rho over g. In other words, dm dx is equal to rho over g. So plugging this value in here is going to give me m, or not m, sorry, rho over 2 dx dt, which is exactly our velocity. So we have rho over g times v. And that's really helpful because now we have dm dt plugging it back into here in terms of both. Okay. So let's go ahead and plug this back in. Okay, so we have dv dt is equal to, looking back at the original one, dv dt, let's express that in terms of x as well. So we know dv dt is actually equal to dv dx dx dt, which is also equal to velocity times dv dx. Okay, so now we have dv dt in terms of v and dv dx. We have dm dt in terms of v. And so now with this combination, we can go to our force equation and make some magic happen. So we know that mg equals rho x, which is equal to mv dv dx plus rho g over v squared. Okay. All right, so let's consider this equation. And it looks like m we can also express as, so we have rho x equal n, we know is the same thing as rho x over g dv dx plus rho gv squared. That's really handy because now I see a common factor of rho I can reduce to 1. And let's see. I think this becomes a Bernoulli equation is what it looks like. So the rows cancel, so I'm left with, let's see, left with x equals x over g dv dx plus, oh, it's gone, plus rho over g squared. Right, so if I divide by x over g and rearrange, I should get, let's see, dv dx plus 1 over x v equals g over v. I forgot my v. I forgot my v. That's what's looking weird. My v here, and that's what I did about by there. So that makes sense. It's like, how did I get my v down here? Because I didn't reduce the point there. That's what. Okay, that feels good. All right, so is it Bernoulli? Let's see. This is g over v to the negative 1. Yeah, that's Bernoulli. Okay, fantastic. I was not expecting a Bernoulli into this. So let's solve it. Kind of fun. I didn't expect to go there. All right. So let's let what? W. I'll go with W. W equals V, so 1 minus 1 equals V squared, which implies, of course, that V is equal to W to the 1/2 of the square root of W. dV, no, why did I write W? That's fine. dV dx is equal to 1/2 W to the negative 1/2 dW dx. Okay. All right, let me go ahead and switch boards here, and we can now rewrite the entire equation and solve, plugging in to the original, plugging all that back into the original. So we have 1/2 W to the negative 1/2 dW dx plus 1 over x W to the 1/2 equals 2 over W to the 1/2. That's a good sign for a Bernoulli equation. If I multiply everything through by W to the 1/2 and 2, yes, looks like both, yeah. We'll multiply everything through by 2W to the 1/2. Cancels, makes the W, and it's a 2. Okay, so we get W to W over dx plus 2 over x W equals 4. G. No, and G's are looking like 2's. That's horrible. So this is going to be 2G. Looking at my, yeah, that's a G. I thought it was a 2. Looking back here at my previous board, there, I thought that was a 2. Go figure. Huh. It's like, where did 4G come from? Our 4 component should be 2G. All right, so there's a 2G. Okay, so now this is just an integrating factor problem. So we have e to the 2 over x dx. So it's going to be e to the natural log of x squared. This is going to give me x squared. Okay. All right, so I get x squared w prime is equal to 2gx squared. Okay, integrating. It's going to give me x squared w is equal to, looks like 2/3 g x cubed plus a c. Divide through by x squared, get w is equal to 2/3 gx plus c over x squared. And remember, w was Oh, that was W. All right, W. W was equal to B squared. So W is equal to B squared. Yeah, so this is going to be B squared equals 2G over 3X plus C over X cubed squared. And let's see, what was the initial conditions? At, yeah, 10 feet, X is 0. Sorry, T is 0, V is 0, X is... Okay, so to find the C, we know that X of 0 is equal to 10. V is equal to 0. Okay, so let's plug that in. V is 0. V is 0 is equal to 2G over 3 times 10 plus C over 10 squared. So solving for C, you get negative 2000 G over... Okay, yeah, that's right. And so finally, I guess we could approximate G is equal to 32 feet per second squared, since this is in feet. Roughly speaking, that is true. And the C's now have a 3 in common. So if we factor out, so V of T squared is equal to, we get 64 over 3, factoring out the common values, X minus 1000 over X squared. But not the exact result you might have expected from a situation like this, but it does seem to make sense overall. So that's the speed of the chain as it falls. That's the function that determines the velocity at a point X along the chain falling from the windowsill. Okay, that was a lot of fun. Kind of clumsy stepping through it, but I think overall it made a lot of sense. Okay, I think that was all of the notes and their problems. Okay, I hope that was helpful, and I will see you in the next video.